Now we know that capacitors can store charge. So basically, we're defining a capacitor as some element in a that's in an electric field that will hold charge. And we define its capacitance as the amount of charge it has divided by the voltage on it. For two plates, that is sigma, that is epsilon 0 A over D, but it doesn't need to be two plates. And for the other geometries, it won't have that same form. There'll be other forms, and we'll look at some of that a little bit later on. But what I want to do right now is say, okay, so this capacitor is storing charge. How much energy is it storing? And we work this out in class. I'm going to actually do it a different way right now, and you guys are, you can compare this to the other way that we did in class and see that they end up with the same result. Okay, so let's just start with some plate. I've got a uniform plate here, and it has an electric field, which you guys know from the Gauss's law stuff we've done, and from actually much earlier where we integrated dq by dq, we know that this field out here is sigma over 2 epsilon 0. We know it's for positive charge. We know it's in this direction, so I'll go ahead and make that an x-hat direction. Okay. All right. So this is our electric field. Well, we also know that our electric field is also equal to minus delta V over delta X, and it is delta X in this. In this geometry, it's delta X because all the symmetry is lined up in that way. So I know that I can compute my 2 epsilon 0 by doing, this is E dot dl, but the delta x and x are in the same direction, so I'm just going to write delta x, and this is going to equal the minus gradient of this. Okay, so what does that mean? That means that if I were to plot what this looks like versus distance, I would have a voltage. Let's just say that. I would have a voltage that goes to here, it goes in this direction, and the slope of this is going to be minus sigma over 2 epsilon 0. And the minus just means it's a downward sloping line instead of an upward sloping line. And what do? You guys know in class that the delta V here, I've kind of pulled a little bit of a fast one on you because I changed from delta V to V, but the reason I did, or the way I did that, is I said, I'm just going to make this be equal to 0 way out here at x equals infinity. I'm going to make that equal to 0. And therefore, as long as this is 0, I can now talk about V in absolute terms rather than in relative terms. So our voltage is that. Okay, so now the question is, what would happen? How much work, how much energy would we gain? Yeah, that's the way to say it. Or how much work would it take to take a plate way out here, a negatively charged plate. Oops, that's probably not on your screen. I can't tell because my computer screen has turned off. But so a negatively charged plate that's way out here at infinity. What if we take this and I probably needed some of that, but that's all right. What if we take that and move it all the way into here to some point x1. Okay, so some distance x1 away. So what's the amount of energy that we are going to gain or lose? Well, what's the potential energy difference? The potential energy difference, we start out at Q sigma over 2 epsilon 0 times x. I'll go ahead and say x infinity. So that's our initial. Our final potential energy is Q sigma over 2 epsilon 0. Oops, there's a minus sign in front of both of those, as you guys will, well, here it is. I was going to say you'll recall, but it's right there. Sigma x, so x1. All right, so this is my change in potential energy. When I go from way out at infinity and I bring this way into, when I bring it right next to here. This is my change in potential energy. Now, if I'm, I'm sorry, it is the amount of work I'm doing on the system which increases the potential energy, okay? So I'm kind of playing a little bit fast and loose, but you guys understand that QV is our potential energy at one point, and so if I go from QV1 to QV2, I'm changing them to potential energy. Okay, so how am I changing that potential energy? Well, the answer is that I am, what do we say this was equal to? We said the potential at infinity, we're just saying that's equal to 0. So this goes away. And so what am I left with? I'm left with this. I'm left with Q sigma over 2 epsilon 0 x1. And this is now positive because I've got negative and negative, which canceled. All right. What is Q? I'm sorry. Yeah, is that the way I want to go here? What's the... I think that's the way I want to go here. Let me think about that just for a second. Oh, yes. Okay. So let's try this. Q is... the Q here is the exact same Q as we have here, except it's the opposite sign. So our Q is just sigma A. So when I end up here, let me see if I can... Actually, is that the direction I want to go? No, let's do something else. Hang on, let me see what I did when I did this. Yeah, okay. So let's leave that as Q and instead do the opposite. Let's go like this. Let's multiply this by A over A. And then what do we have here? We have another sigma A, which is Q. So what we really have here on top now is Q squared. Q squared. And I'm going to change this to our big Q since that's what I've been saying before for the charge on a plate. So we have Q squared over this 2 epsilon 0 A. X1. What's X1? X1 is just D, the distance between these two plates. So I'm just going to change that to D. Now, what is epsilon 0 A over D? I'm not sure that you're seeing that. So, okay, what is epsilon 0? What is epsilon 0 A over D? You will recall this is our capacitance. So what have we just discovered here? We have discovered that we have changed the energy by 1/2 Q squared over C. And you will recall, well, if you were in class, you will recall we got the same result before for the energy stored in a capacitor. So this, I'll go ahead and call it U. Energy stored in the capacitor, we had that same result before, deriving in a completely different way. Okay, but this way works just as well. I just wanted to show you that. So now you know a new way to determine the energy on a capacitor.